Hi everyone, thank you for joining today's webinar. In this session, we'll be replaying one of our most popular webinars to date. Andy Liu, LucidWorks Senior Data Scientist, has presented this webinar in the past, and today we'll be replaying the recorded session for you. At the very end of the webinar, we will have special guest, LucidWorks Chief Algorithms Officer, Trey Granger, on the line to answer your questions live from the audience. In today's webinar, you'll learn about Solr and Fusion's learning to rank capabilities. We encourage you to enter any questions you have throughout the webinar in the Q&A chat box on your screen. At the very end of the webinar, Trey will answer your questions live on air. If we don't have a chance to answer your questions today, a member of the LucidWorks team will reach out to you. Thanks again for joining, and we hope you enjoy the webinar.
Thanks for joining, everyone. Let's start our webinar today by thinking about the problems with classic models of relevance. The core algorithm of search is called TF-IDF, and Solr uses an algorithm called BM25 that improves upon TF-IDF, but the basic idea is the same. If a distinctive term appears more frequently in a document, then that document is more relevant for that term. This is good enough for most searches of most document collections. However, there are times when just looking at keywords are not enough to accurately capture user intent. To illustrate, let me show you an example that Chao Han, our VP of Data Science, gave in our last webinar. Imagine that a user searches for outdoor rock speaker and sees the results on the left. The search results are ranked according to how often these words appear in these particular documents in the way that you would expect. However, the term rock is ambiguous. Depending on the context, rock can refer to a type of music, or it can be a geological term. So it turns out in this case that the user actually wanted a speaker shaped like a rock, something that looks more like the results on the right. This is an example of a keyword search that does not match user intent. To summarize, Solr and Fusion's default BM25 algorithm is a good general-purpose scoring model. Improving upon it is somewhat difficult, especially in a global, systematic fashion, and not in an ad hoc, case-by-case, whack-a-mole basis. But perhaps for your enterprise, there are many valuable business-specific, non-keyword-based relevance factors you want to leverage. In these cases, keyword search just isn't enough. So one of the ways Fusion 4 and Solr 7 allow you to address this problem of relevance is through an algorithm called learning to rank. Learning to rank is a machine learning technique where we teach the computer how to rank items. We do this by choosing features, which you can think of as relevancy factors, that we think the algorithm should weight and tune. We also need a source of ground truth or order. One source of this is user behavior. Luckily, Solr provides some nice basic building blocks for implementing learning to rank. And meanwhile, Fusion provides a way of capturing user behavior as well as pipelines for applying these techniques. In order to understand learning to rank, let's draw an analogy from the problem of spam classification, which everyone is familiar with. The goal of spam classification is to accurately predict whether or not an email is spam on the basis of different characteristics or features of email. Interesting features that could provide clues as to how spammy an email might be, the kinds of words it contains, or perhaps the number of URLs it contains, or whether or not the email is from a known user. So machine learning is used to learn a function is spam, which is trained using existing emails in order to generate predictions for new emails with a high degree of accuracy. Similarly, in the learning to rank model, instead of using machine learning to predict spam, we use machine learning to predict whether or not a query, like iPad, is relevant to a document. The features used to feed the model are similar kinds of relevance factors that you would use to feed a Solr ranking function. Things like the score of title matches or the score of body matches, or perhaps the number of views a document has. Similar to how a spam classifier learns from training data in the form of emails, learning to rank models are trained in the same way, but with ground truth relevance labels. Fusion offers a powerful and convenient platform for building learning to rank models. In particular, Fusion Signals captures user behavior like user clicks, queries, and other details. These signals are captured either automatically if you are using our App Studio products, or programmatically otherwise. Either way, signal events are sent to Fusion via a REST endpoint as JSON, and these events are captured by Fusion in a special type of collection called signals, and periodically aggregated into aggregate signals for efficiency reasons. By default, Fusion uses these to boost documents that are more often clicked or purchased for a given query. Learning to rank is able to turn these signals into improved relevance by using state-of-the-art machine learning algorithms to automatically blend user behavior signals with more traditional textual relevance factors. This algorithmic blend of text and context potentially offers superior search relevance with far less manual tuning. So what do you need in order to get started with learning to rank? First, we need to decide on which features to feed the model. You could think of features as relevancy factors like title match score, body match score, or signal-based features. Next, we use Fusion Signals to create ground truth from clickstream data. Ground truth is simply a large list of queries and the most relevant documents for each query. Lastly, we use Solr's learning to rank implementation to help us train a learning to rank model. Before we get too deep, there are a few things to consider. Definitely try just normal Fusion Signals and boosting before you try learning to rank. It may be good enough or possibly great for your corpus. Also be sure you've done all of your relevancy tuning first. LTR does introduce some complexity, so it is more or less a last mile technique. When using click signals for ground truth, there are some things to be aware of. On one hand, click signals are voluminous, cheap, and on the whole, reflect a user's intent, especially when supplemented with purchase or add to cart events. On the other hand, click signals can be noisy because users tend to click the first result and not even notice the second result, so this can self-reinforce what your keyword search was doing anyhow. The alternative to using click signals for ground truth is to produce them manually or through crowdsourcing, which is more expensive, but also more accurate. Let's look at how you do this in an overview. So I'm not going to go over this step by step, as we have a technical paper that already does that. Instead, we'll just look at the bigger picture of how the parts fit together. So here's the big picture workflow for how to implement learning to rank. In this diagram, I'm just going to start with step number 1 in the lower left and follow where the arrows point. So number 1, we upload a set of features via Solr's JSON REST API. Next, using Fusion Signals, we produce a ground truth ordering of our results. And once we have that, we can use a Spark job to extract feature vectors for each query. Number 4, the feature vectors are then used to serve as input to the LTR model trainer. Number 5, once the model is trained, we upload it to Fusion. And 6, lastly, a custom Fusion query pipeline will handle future user queries. And when they query again, they'll see the results in the order provided by our learning to rank model. If you grab the technical paper from our website, it will walk you through implementing this using the Best Buy dataset. which you can download from the Kaggle website. In the sample code provided, I run the full end-to-end LTR training pipeline to train a few different models, namely straight out of the box Solr on textual features only, the logistic regression model using all features except signal features, and a logistic regression model using all features including signal features. The performance metric I use in this graph is recall at 5, which is simply for a given query, what percentage of relevant documents appear in the first 5 results, averaged over all queries in a held-out test ground truth set. The signal feature used applies a query-aware boost to documents that are more frequently clicked or purchased. The learning to rank model will automatically weigh this feature along with all other textual features in order to maximize relevance according to our metric. As you can see from the graph, there are significant relevance improvements observed over out-of-the-box Solr BM25 ranking, and even over the logistic regression trained model when using signal features. While the goal of this tutorial is to demonstrate how to implement learning to rank, and not necessarily how to produce the most accurate model, it's nice to see that leveraging fusion signals can easily yield significant gains in relevance, even when we use them in a relatively casual way. So let's sum up the key benefits of using LTR. Using learning to rank offers us a way to automatically tune relevance. Meanwhile, using fusion signals, pipelines, and job management reduces the time and complexity required to train and deploy LTR models in production. Using fusion signals, you can do learning to rank and provide better results than keyword search alone. With all that said, do all of this carefully. Fusion 4 includes an A/B testing facility that will let you see whether LTR is better for your data set with your use case. A/B experiments work by directing a subset of your traffic to the new LTR pipeline and seeing if more users found what they needed. If you're interested in trying learning to rank on Fusion, grab the technical paper from our website, and you'll also find the code required in our GitHub repository. Thanks for joining, everyone.
Great. Thanks for sending in your questions throughout the webinar. Before we get into the live Q&A with Trey, we want to quickly announce that Activate, Lucidworks' annual user conference focused on leading search and AI trends, is just a few weeks away. Activate will be held in Washington, D.C. from September 9th through 12th. If you're interested in learning more about trending AI and machine learning techniques that can help transform your digital experiences, please join us at the conference. You can hear from experts in the field, including Andy and Trey from Lucidworks, along with other experts from companies like Uber, Airbnb, Target, and many more. Check out the Activate website and agenda to learn more. We hope to see you there. And without further ado, I will now pass it over to Trey to get started on answering your questions that were sent throughout the session. Keep in mind, we still have some time to answer more, so please enter in your questions for Trey now using the Q&A chat box on your screen.
All right. Thanks, Janessa. Thanks, everybody, for joining. Janessa, I think I see some questions coming in. Maybe if you want to read off some of the questions, I can handle the answer part. Does that work for you?
Yeah, of course. So we have one question here. It says, I've heard the phrases learning to rank and machine learning and machine learned ranking, both used before to describe these capabilities. Is there any difference between them?
Yeah, no, that's a common question. No, they're actually exactly the same thing. So depending upon what website or person you're talking to, you might hear them say machine learning ranking or learning to rank. But yeah, but both are used interchangeably.
Great. And we have another question here. It says, what's the difference between signal boosting in Fusion and learning to rank? They both seem to be improving relevancy based upon signals data. Are they doing the same thing? And if not, can they be both used together?
Sure. So they they both leverage the same underlying data, but they actually serve two different purposes. Actually, I think I might, let me see if I can share my screen. I've got a slide I can, yeah, show it this way. So if you see the slide currently on there, you've got this notion of feedback loops. So both learning to rank and signals boosting are different mechanisms for leveraging feedback loops. So feedback loop basically is a user runs a search, they see some results, they click on or take some action based upon those results, and then those actions are used to build models that will influence future results. And then the next user who comes in will run a search, their results will appear different based upon that model, and you just have this constant feedback loop where things are hopefully improving over time. And so signal boosting, if you sort of look at what you see on the screen here, the formatting is a little weird, so bear with me as I'm pulling these up on the fly. But with the signal boosting model in Fusion, effectively what we're doing is through that feedback loop. If you sort of look at the query example on the screen where somebody searched for pizza, that search for pizza gets logged. So sort of each user, you see here, Alonzo search for pizza, Elena search for soup, Ming search for pizza. Those searches get logged, and then whenever those users take subsequent actions, maybe clicking on documents or purchasing or what have you, those signals are recorded. And then ultimately those signals get aggregated into a model that says, for a particular query over here on the left, for example, pizza, this particular document was very commonly clicked on or very commonly purchased. And so what ends up happening is you build this aggregated model where for particular queries, there's specific items that users tend to prefer. And so that model then gets used on the next search, which you'll see back at the top. So the next time somebody searches for pizza, document 22 in this case and document 12 get boosted. So signal boosting is focused on understanding which specific items in your result set users like and making sure those come back for a query. Learning to rank, on the other hand, is used to learn a generalizable model. So in the case of learning to rank, here's a similar slide for learning to rank, and yeah, the formatting's kind of messed up, so I'll just explain it. When someone searches for pizza, the same searches and click signals get logged, but ultimately, instead of generating a list of specific items to boost, the learning to rank model, which you'll see in the bottom left, is learning which features of the documents or of the queries mattered. So in this case, you'll see that things like whether there was a title match, that got a very high weight. Whether the query was in a known category, that got a high weight. The popularity of the document got a high weight, and the content age got a high weight. And then that model gets deployed to the search engine. So with learning to rank, you effectively, now for new queries in the future that I've never seen before, they've learned the relative weighting of relevance factors. And so, just to kind of sum all that up, and I think I'll rely on these slides a little less next time because of the formatting issues. But to summarize that up, learning to rank is good for learning a generalizable relevance model that will apply to all of your queries, whereas signal boosting learns specific boosting of specific items for queries that are popular with your users. And so learning to rank can better handle unknown queries, whereas signal boosting works really well for well-known head-tail queries.
Great, thanks, Trey. We have another question that came in. It says, how fast will learning to rank generate a new model for improved results? How often does learning to rank run to update the model?
Yep, also a good question. So the answer to the last question will actually dovetail into this a little bit. So I talked about how signal boosting is based upon specific items being boosted for queries. So for signal boosting, you want your signals to be up to date as soon as possible so that current user actions can affect searches very quickly. Often for learning to rank, you actually don't need to rebuild the model as often because, again, you're learning a generalizable model. And in most domains, the relative weighting of relevance factors doesn't change that often. Specific documents might become more important, but you've learned a relevance model for the things that are in the content. So even if you've got content constantly changing, those relative factors won't change that often. So long story short, usually you don't have to update your learning to rank model that often.
Great, thanks. One more question. We have, how many signals does learning to rank need to capture in order to generate a model that will make a difference in relevance?
Sure. Let me think about that. So it's a good question. So you can actually train a learning to rank model either by having a human go and manually create relevance judgments, basically saying for this query, this document is relevant, this document is less relevant, et cetera. Or you can use signals to automatically generate these relevance judgments. Explicit judgments, you don't need as many because you know that they're accurate, but whenever you're dealing with signals, if I only have, a query that has, 1 or 2 searches or even, 1 or 2 clicks, it's very hard to generalize from that little bit of information whether, the user's clicks were actually an indication of relevancy. As you get more and more signals, you can tend to generalize that better. And the general intuition there obviously is when users run searches, the documents that they click on tend to be documents that they at least perceive to be more relevant. And the ones they skipped over would be the ones that they perceived as less relevant. So, 1 or 2 is definitely not enough. If you've got sufficient queries, maybe by the time you get to, 20 or 30 signals for a particular query and, specific documents, that might work. Certainly, the model will get better and better as you get into the thousands. And so definitely the more data, the better the model is going to be, and it's going to help you overcome some of the noise that is inherent in click streams. The one thing I will point out is that typically when you're using signals to generate judgments for learning to rank, you're going to focus more on the head queries and some going into the torso. So the things people search for and interact with and click on documents for a lot. Because usually in the less common queries, the same model that you learned for the head will often apply in the tail. So usually you focus on where you have more data, and any queries that have a very limited number of searches or a very limited number of clicks, you probably want to kind of throw those away and exclude them when you're generating your training data.
Awesome, thanks. Another question here, it says, actually, I would like to hear more about the machine learning model that was used. Was a deep learning model involved or feasible for learning to rank?
Sure. So Andy mentioned a white paper that you can go check out. I'll also share that he mentioned also that there's a GitHub repo where you can actually go and download Fusion, download Solr, and actually build these models and go through Jupyter notebooks and work on it. In that particular case, it was pretty simple kind of logistic regression model. It was basically figuring out based upon searches and clicks, for documents that were clicks on, they were deemed relevant. For documents that there weren't clicks on, they were deemed irrelevant. And it was sort of a binary classification model to ultimately generate weightings for specific features he came up with. It's a pretty basic model, and it's useful for learning how learning to rank works, and if you're trying to sort of optimize your own relevance ranking function, possibly even independent of learning to rank. But in general, in learning to rank, there's a lot of different approaches you can take. There's kind of 3 essentially. There's a point-wise model, which focuses on trying to predict a score for a single document at a time, with the idea being you can sort of try to predict a relevance score based upon the combination of features. So that's point-wise. There's pairwise models, which try to optimize for 2 different documents. Anytime you see 2 documents, you want them to, if one's more relevant than the other, you're trying to minimize the number of times that the less relevant document appears above the more relevant document. And then there's this idea of a list-wise model, which is typically optimizing directly for some search metric like NDCG or expected reciprocal rank or something, or sometimes even conversions if you've got historical data. In which case you're trying to look at the entire set of search results at once and optimize the ranking of that list. And so you can apply. There's a lot of popular models and libraries out there, like XGBoost and RankLib and things like that, that have different combinations of support for pointwise, pairwise, and listwise models. There's deep learning models in there as well, but I guess if you zoom back out a little bit, there's not one way to do learning to rank. Learning to rank is essentially building a ranking classifier that can take queries and documents and try to come up with the best ordering of them. And so, yes, you can use deep learning models, but there's a lot of simpler models that don't require deep learning that also perform well.
Great, thanks. We have another question. It says, how would this help in an e-commerce setting? Suppose I have a query of pants and another query for trousers. Will the sorts be different or will it be the same? How would you achieve this with learning to rank?
Yep, good question. So learning to rank is one of many techniques that you'll use in search. It's typically used to try to figure out relative ranking of documents. In your case, you're talking a little bit more about a sort of semantic search approach. And so if I zoom out, though, from a learning to rank standpoint, a search for pants, if that's actually in my training data set, versus a search for trousers are likely to return similar results. But there's probably some slight differences where users would expect certain documents to rank higher. So in your training set, the data is going to learn generalizable features from both of those, but because they're similar terms, you're probably going to end up with a learning to rank model that doesn't differentiate between the two that much because they're just inputs to the training set. And if you trained a model that didn't include those two examples, they're keywords that then map to your content. And so I would say that generally speaking, learning to rank is not going to help you differentiate between those two as much. Versus if you go with something more like a semantic search approach, which understands terms and phrases and how those get rewritten from tail queries to head queries, which is something we also have in Fusion. That kind of an approach would tend to work better. So learning to rank isn't the only way to improve relevance for search. It's one of many tools in your toolbox. I would say that for things that are highly nuanced understandings of queries and how they're interpreted, I would look at something more like the semantic knowledge graph, which is available in Fusion and Solr, as opposed to learning to rank for that specific problem.
Great, thank you. Another question here, it says, how often do I need to retrain my model, and what's the best way to monitor my model's performance?
Sure. So they didn't say for performance whether they meant sort of quality of results or whether they meant speed of the query. I'll try to answer both. So in terms of, sorry, Janice, can you repeat the beginning of the question again, just to make sure I got it?
Sure. How often do I need to retrain my model? And what's the best way to monitor it for performance?
Got it. Okay. So in terms of retraining your model, we've got some customers who, retrain once a week, some customers less often. If you've got a workflow where it's conducive to you running it more often, you can. But going back to my comments from earlier, typically a learning to rank model is learning a generalizable relevance function that you can apply across either your entire data set or subsets of your data set. So unless your a vast majority of your content is changing very frequently, or there's some substantive change in what's going on in your search platform, you really don't need to retrain it that often. But it is good practice not to just train it once and deploy it and then come back 6 months later. It's a good practice to have a workflow where you can retrain the model whenever you need. So I would say you should definitely build something that allows you to retrain as needed, but there's no need to be running this hourly or even daily, or in a lot of cases even weekly. It depends on your use case. In terms of monitoring performance, if you're talking about quality performance, the best way to do that is to have really good analytics around whatever your business is optimizing for. So if you're in e-commerce, for example, you're going to be optimizing for your likely conversions or average order value or something like that. you want to keep active monitoring of those things to make sure it's not going up or down. But then the real thing you want to focus on is A/B testing. So, just because you trained a learning to rank model and you deployed it to production doesn't mean your results are going to get better. If the model itself is bad, or if the training data was bad, or if you have some sort of a garbage in, garbage out scenario, or even if your feature engineering wasn't great, you could actually end up hurting performance if you're not careful. So it's really important whenever you go to actually deploy an update to your learning to rank model that you do A/B test it with what was there before and what's and the new model, just to make sure that performance is the same or ideally better than what you had before. In terms of if you're by performance, you were talking about speed of queries. Again, that's a monitoring issue where your ops team it hopefully has monitors around the performance of your system. And most teams, if you've got a larger team especially, will have a staging area where you can actually run load tests before you deploy something to production to make sure that there isn't a noticeable increase in latency that could potentially either bring your site down, bring it to a crawl, or could cost you a lot in additional servers if you're auto-scaling or something like that. So effectively, you just need to have good monitoring around whatever you're deploying and test it before you deploy it 100% to production, just like with any good software change.
Great, thanks, Trey. Another question here, it says, is there any component that we need to build outside of Fusion to build our learning to rank model, or is Fusion self-sufficient enough to build this end-to-end?
Yep, that is a great question. So Fusion obviously includes Solr, and Solr is the core information retrieval engine in Fusion. As you saw in the webinar, you can actually deploy your learning to rank model to Solr, and so Solr provides the base ability to re-rank results. On top of that, though, Fusion provides the ability to create document-level features through index pipelines, query-level features through query pipelines, to turn on the invocation of different learning to rank models and A/B test them. Fusion also provides the ability to collect signals, to aggregate those signals, and even to generate the ground truth training data set that you can use to then build your learning to rank model. And also, manage and schedule kicking off the training jobs, coordinating the model updates that typically get pushed to Solr, and ultimately managing that end-to-end process for learning to rank. We also include an ability in Fusion to be able to back test your LTR model, so you can sort of do an offline test before you actually have to go to production to see what the likely increase in relevance or conversions or NDCG or whatever metric you're using is. So Fusion does provide a pretty much end-to-end platform for being able to deploy and run and test your LTR models. The one thing that is not directly in Fusion currently is the actual training process for the LTR model. So for example, if you're picking a deep learning model, or if you're picking a logistic regression model, or if you're picking whatever model you're choosing, typically speaking, you're going to have someone on staff, a data scientist or somebody like that, who is going to make that choice and then use their tool of choice, whether they're using RankLib, TensorFlow, what have you. We've got full support for lots of different learning to rank libraries, but typically you're going to be training that offline. So if you look at the GitHub repository that we referenced in the presentation, you'll see some Jupyter notebooks there that actually go through the process of training the model like a data scientist would do. That one piece we don't have directly in Fusion because most of the time you're going to want to have control over that and making those choices. But once you've made that choice, the whole process for deploying and operationalizing and testing that model is fully included in Fusion.
Awesome, thank you. And thanks everyone again for putting in your questions to the chat box. We have time for maybe one or two questions left. So let's get started with answering the last two here. So we have one question that came in. It says, how does manual tuning work with learning to rank's effect on ranking, which is something you kind of already talked about, Trey. How do you balance both to ensure you don't degrade the combined overall results?
Sure. So one thing we didn't talk about as much in this presentation was the actual process of re-ranking with learning to rank. So typically, whenever you're applying a learning to rank model on queries, it's a two-phase process. The first phase is running a cheap query. That's typically using the built-in similarity, which is BM25 in Fusion and Solr by default, or some other TF-IDF-based ranking model. Those are very, very fast and efficient at finding a generally good set of results. Once that set of results is found, learning to rank models are then applied as a re-ranking step. So what that means is that while you might run a search for a particular query, let's say trousers, and you then get a million results that come back, out of those million, you might take the top 100 or maybe the top 1,000 results and then pass only those to the learning to rank model to re-rank them with a much more complex ranking. So in terms of manual relevance tuning, that is going to be applied to that first phase, which is generating all of the possible results that could come back. And the learning to rank model is typically going to be applied in that re-ranking phase, which maybe applies to 100 or 1,000 results. And so it's still a good idea to make sure that your base ranking function is reasonably well tuned to make sure you get the best results coming back to be re-ranked, because the last thing you want is to be re-ranking a set of 1,000 results or 100 results that are already irrelevant, because then the learning to rank model is not going to help you. So you do need to make sure you've got both stages of that reasonably well tuned.
Great, thank you. And this last question here, we'll wrap up the webinar. This person asked, do you have any data comparisons with other similar ranking/personalization products? One, for example, is AWS Personalize.
I don't personally, off the top of my head, have that. I could check with our marketing team and see what we have. They can probably follow up with you on that. Learning to rank is not new. It's been around for decades in terms of literature and in terms of research, and there's lots of different libraries. Solr was the first open source platform to add learning to rank back, I think, in 2017, with people working on it before then. What we do in Fusion basically provides you the full operationalization of that. I don't even know if that's a word. It really depends on the specific model that is being used, and those are going to be chosen based upon your domain and the data that you have and what have you. So it's not a check the box. Learning to rank in general performs this well. It really is based upon your data and the models that you choose. So it's kind of hard to answer that abstractly, but certainly on a case-by-case or customer-by-customer basis, we could dive into that more offline.
Awesome. Thanks, Trey. And that wraps up the Q&A. So we hope you enjoyed the webinar. Trey, thank you again for getting on live to answer the questions from the audience. If we didn't get to your question today, a member from the LucidWorks team will reach out to you. And again, if you have any other questions or want to chat with one of the members at LucidWorks, feel free to contact us through our website. Thanks again, Trey, and I hope everyone has a good rest of your day.
Awesome. Thanks, everyone.